students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as Halogen Derivatives of Alkane. Let's see the reactions of alkyl halides. Today we'll start with reactions of alkyl halides. Right, first let's see substitution reaction. What is substitution reaction? It involves substitution of one atom or a group of atoms by another atom. Now let's see substitution reactions involving substitution reactions with aqueous alkali. What happens when ethyl chloride reacts with aqueous KOH? Ethyl chloride with aqueous KOH. Right? Ethyl means two carbon atoms. Chloride is Cl. Ethyl, that means this is going to be CH3 CH2. Right? Ethyl chloride reacts with KOH aqueous. Reacts with aqueous potassium hydroxide, boil and heat. Right? In which case K will react with Cl to give you KCl plus CH3 CH2OH. What you will get is ethyl alcohol. Two carbon atoms, therefore ethyl, OH, therefore alcohol. Right? This is ethyl chloride. So you will get ethyl chloride and ethyl alcohol. Next, let's see a similar reaction. What happens when isopropyl chloride reacts with KOH? Isopropyl chloride with KOH aqueous. Right? Propyl, three carbon atoms. Iso, that means one of the carbon atom has to be in the branch. Chloride, that means Cl. Now this is going to be CH3 CH3 CH Cl3. This is your isopropyl chloride reacts with KOH aqueous. Boil by heating this. Right? Substitution reaction, K reacts with Cl to give you KCl plus CH3 CH2 CH3 CH2OH. So in this case this is going to be equal to isopropyl alcohol, three carbon atoms, therefore propyl, methyl group is in the branch, therefore isopropyl, and OH, therefore alcohol, and this is isopropyl chloride. Right? Next, let's try to see another reaction. Now, when we are doing substitution, you could do substitution even by using silver hydroxide. Right? Besides using potassium hydroxide, the other alkali that is used for substitution is also silver hydroxide. Let's see with silver hydroxide what happens when ethyl iodide with silver hydroxide. Ethyl, two carbon atoms, iodide, I. Ethyl, CH3 CH2I reacts with silver hydroxide, AgOH. How did I get silver hydroxide? If silver oxide reacts with water, that will give you silver hydroxide. Right? This is silver oxide. Boil this, you will get silver hydroxide. Right? Now, once you have this, you will have substitution reaction. Silver will react with iodine to give you AgI plus CH3 CH2OH. Right? This is ethyl iodide and this is going to be 2 carbon atom, therefore ethyl, OH, therefore alcohol. So you will get ethyl alcohol. Fine. So this was substitution reaction we've done using alkali. Let's aqueous alkali. You could also have, you use potassium hydroxide, you use silver hydroxide. You could also use potassium cyanide as an alkali. For example, what would happen when methyl bromide reacts with alcoholic potassium cyanide? Methyl bromide with alcoholic potassium cyanide, KCl. Right? Now methyl bromide, one carbon atom, this is methyl bromide, reacts with alcoholic potassium cyanide. Right? Substitution reaction again, K reacts with Br, potassium reacts with bromine to give you potassium bromide, and that will give you CH3Cl. This is methyl bromide, and this is going to be methyl cyanide. Right? So you will get methyl cyanide over here. Now besides methyl, you could also have this reaction with ethyl. Right? You could also have the reaction with ethyl. So in that case, suppose if I have ethyl chloride reacts with alcoholic potassium cyanide. Right? Ethyl, 2 carbon atoms, chloride, Cl, CH3, CH2 plus KCN, alcoholic. Right? In which case you need to heat the reaction. When you heat the reaction, you will get substitution reaction. K will react with Cl to give you potassium chloride plus CH3, CH2, Cn. This is ethyl chloride, and this is going to give you 2 carbon atoms, therefore ethyl CN, therefore cyanide. So this is going to be ethyl cyanide. Right? Now you could also have substitution reaction by using silver cyanide. Right? For example, what happens when methyl bromide reacts with alcoholic silver cyanide, alcoholic. Right? Methyl bromide, CH3Br, reacts with AgCN, alcoholic. Right? Heat, silver reacts with bromine to give you silver bromide. Fine? In which case you would have CH3NC. Right? This is methyl, 1 carbon atom, therefore methyl. Here instead of cyanide you get isocyanide. So you will get methyl isocyanide. This is methyl bromide. So methyl bromide reacts with silver cyanide to give you corresponding alkyl isocyanide. Fine, do we get this in here? Now this particular isocyanide that you get has a very unpleasant smell. The characteristic feature of this is a carbyl amine having an unpleasant smell. Fine, do we get this thing here? Next, let's see another reaction of this kind. What happens when ethyl bromide with silver cyanide, alcoholic. Right? Ethyl bromide, CH3, CH2, bromide, Br. Ethyl bromide with silver cyanide, alcoholic. Heat. Right? In this case you will have silver reacting with bromine to give you silver bromide, right? Plus CH3, CH2, Cl, right? This is ethyl bromide this is ethyl, and this is going to be isocyanide. Isocyanide, that means this is going to be NC, right? Isocyanide. Fine. So this was your substitution reaction using silver cyanide. You could also have substitution reaction with alcoholic ammonia. What would happen if methyl chloride with alcoholic ammonia, right? Methyl CH3, methyl chloride with alcoholic ammonia, NH3 alcoholic. This particular reaction takes place at 373 Kelvin. So you need to heat the reaction. Substitution reaction, 1H from the ammonia will react with H to form hydrochloric acid, and you will get CH3NH2. You will get amine group. So you will have methyl chloride will react with ammonia to give you methylamine. What you get is methylamine. Next, similar reaction. Let's see what happens when ethyl chloride reacts with alcoholic ammonia. Ethyl chloride with alcoholic ammonia. Ethyl, 2 carbon atoms, chloride, Cl, H3, H2Cl plus alcoholic ammonia, NH3AlC, 373 Kelvin heat, right? So in which case, now you will get in this case HCl plus CH3, CH2, CH3, CH2, NH2, right? So this is ethyl chloride, and this is going to be ethyl amine. Fine. Next, what would happen when isopropyl chloride reacts with ammonia? Right? Isopropyl chloride, propyl, 3 carbon atoms, iso, that means one of the carbon atoms should be in the branch, chloride, Cl, CH3, CH3, CHCl. Isopropyl chloride reacts with ammonia, 373 Kelvin heat, right? Now, hydrogen will react with chlorine to give you hydrochloric acid. This will give you CH3, CH, CH3, NH2, right? So what you will get here, this is isopropyl chloride this is going to give you isopropyl amine. Fine. Okay, next let's see another reaction piece. What would happen when, let's see another reaction of substitution. Suppose if I say, if it reacts with methoxide, if it reacts with alkyl sodium alkoxide. For example, if I have methyl chloride with sodium alkoxide, so sodium methoxide, right? Methyl chloride reacts with sodium methoxide, methyl chloride, CH3Cl reacts with sodium methoxide, metho, CH3, right? Sodium methoxide, right? Valency of oxygen is 2, so one bond will connect with methyl group, one will connect with sodium group, right? Boil this, right? CH3 combines with another CH3. First of all, substitution. Sodium will combine with chlorine to give you NaCl. Once sodium chloride is gone, that means that is going to leave me with CH3O, CH3, methyl, methyl. This is dimethyl. Oxygen in between, ether, right? This is methyl chloride. Fine. So methyl chloride will react with sodium methoxide. This also we write name. This is sodium methoxide to give you sodium chloride plus dimethyl ether. Right? Let's see another reaction of this kind. What happens when ethyl methyl ether? No. What happens when ethyl chloride? Ethyl chloride reacts with sodium methoxide. Right? Ethyl chloride CH3 CH2 Cl. Ethyl chloride reacts with sodium methoxide. Metho CH3 sodium NaO, sodium methoxide. This is ethyl chloride with sodium methoxide. Right? So heat and boil, in which case you will get this as NaCl, sodium chloride, right? This is going to give you, once this is gone, that will give you CH3, CH2O, CH3. ROR is ether group, E comes before M, so this is ethyl, methyl, ether, right? So ethyl chloride reacts with sodium methoxide to give you ethyl methyl ether, right? Next, let's see another reaction. What happens when it reacts with silver salt? For example, if you have silver acetate reacting with methyl bromide, silver acetate with methyl bromide, right? Silver acetate with methyl bromide, silver acetate. So acetate group is HCOO. This is my silver acetate, right? Reacts with methyl bromide, CH3Br. So this is, wait, I made a mistake, right? Acetate is CH3CO. Acetate is CH3COO. Silver acetate reacts with methyl bromide. Now, silver acetate reacts with methyl bromide. You will have AgBr. You will have silver bromide. Plus substitution reaction, you will have CH3COO, CH3, right? So in that case, you will have CH3 is methyl, CH3OO is acetate group, you will get methyl acetate. This is silver acetate, methyl bromide. Let's see another reaction. What happens when silver acetate reacts with, silver formate reacts with alcoholic methyl bromide. Right? Silver formate, silver Ag, formate HCOO. Silver formate reacts with methyl bromide CH3Br. Right? So this is silver formate reacts with methyl bromide. Right? In which case you will have to heat this. You heat this, you will have substitution reaction. Ag will react with Br to give you silver bromide. Methyl group goes in, so you will have HCOO. Formate group reacts with methyl. So this is going to be methyl formate. Right? Next. What happens when silver acetate reacts with ethyl chloride? Silver acetate with ethyl chloride. Right? Silver acetates, Ag, acetate, CH3COO reacts with ethyl, CH3CH2Cl, heat. Right? Now, silver will react with chlorine to give you silver chloride. This is CH3COO C2H5. C2H5 is nothing but ethyl. This is your C2H5 that I am getting from your ethyl chloride. Right, this is ethyl, and CH3COO is acetate, so you will get ethyl acetate. This is silver acetate. Next, what happens when silver propionate reacts with ethyl chloride? Silver propionate. Propionate means 3 carbon atoms. That means you will have C2H5C double bond O. This is your propionate group. Silver propionate, therefore it has 3 carbon atoms. So silver propionate reacts with ethyl, CH3CH2. That's my ethyl group. Chloride. Heat. Right? So in that case, silver reacts with chlorine to give you AgCl. Right? So you will have the ethyl group that will be substituted here. So you will have C2H5COO C2H5. This is silver propionate. This is ethyl chloride. This is ethyl propionate. Finally, get this. So these are the different types of substitution reaction that you can have. In all of them, you were substituting the inorganic element with the organic element, right? The next type of reactions that you have, first is substitution. The second type of reactions that you have are called as elimination reactions. That's the second type of reaction that you have, right? Now, what are elimination reactions? Elimination reactions are those reactions in which an atom or a group of atoms is removed from adjacent to carbon atom. An atom or a group of atoms attached to the carbon atom is removed, then such a reaction is called as an elimination reaction. Now, in elimination reaction, the first kind of reaction that you have is called as dehydro halogenation. Dehydro halogenation. As the name suggests, if D, removal, hydrogen, halogen. That means it is a reaction in which one hydrogen and one halogen will be removed. Right? So a reaction in which one halogen and one hydrogen is removed is called as a dehydro halogenation reaction. Right? Let's see a couple of dehydro halogenation reactions. What happens when ethyl iodide reacts with potassium? Ethyl iodide with potassium hydroxide alcoholic. Question. So you did the same reaction in substitution also. There also you reacted an alkyl halide with potassium hydroxide. What is the difference? There you had aqueous potassium hydroxide. Here you have alcoholic potassium hydroxide. Right? Ethyl CH3CH2 iodide I reacts with KOH alcoholic. Dehydro halogenation. That means I have to remove first the halogen. How do I remove halogen? This will be potassium iodide. So potassium reacts with iodine. So your halogen is removed. Now hydrogenation. That means I have to remove one hydrogen. OH reacts with one H to form water molecule. OH reacts with one H to form water molecule. That leaves me with CH2 double bond CH2. Right? This is ethyl iodide gets converted into 2 carbon atom, therefore ETH, double bond, therefore ENE. This is also a method by which alkyl halide gets converted into alkene. Right? So ethyl iodide gets converted into ethene. Next, let's see another reaction of this kind. Propyl iodide reacts with propyl iodide with alcoholic potassium hydroxide. Right? Propyl, 3 carbon atoms, that is CH3, CH2, CH2. That's my propyl iodide reacts with KOH alcoholic. Right? Boil the solution. Dehydro halogenation. Remove a halogen. Potassium reacts with iodine. Halogen is removed. Hydroxyl group reacts with hydrogen to give you H2O. Right? That leaves you now with CH3C. That means 1, 2, 3, 4 CH2. Propene. This is propyl iodide. Right? So propyl iodide reacts with potassium hydroxide to give you propene. Now let's see another reaction. Let's consider if you had butyl bromide. You had sec butyl bromide. Butyl bromide with sec butyl bromide with KOH alcoholic. Butyl, 4 carbon atoms. Sec, that means OH is going to be attached to the second carbon atom, right? Not OH, sorry, bromine. It's not alcohol, it's bromide. So CH3, CH2, CH3, CH. This is your sec butyl bromide. Reacts with KOH alcoholic. Now guys, in this case, if I'm going to do dehydro halogenation, the removal of halogen is very simple. The question is, from where do I remove the hydrogen atom? Should I remove it from here or should I remove it from here? From where do I remove hydrogen atom? This is explained to you by a rule called as Sator's rule. Right? Sator's rule says that in case of dehydro halogenation, the hydrogen atom is removed from that carbon atom which contains less number of hydrogen atoms. Hydrogen atom will be removed from that carbon atom containing less number of hydrogen atom. The exact Sator's rule says that in case of alkyl halides, hydrogen atom from the adjacent carbon atom carrying less number of hydrogen atoms is preferentially removed. That's in terms of exact term if you want. Right? Yeah, I'll read that. First let me just show you the reaction, then I'll dictate that too. Right? This is your sec butyl bromide, so in which case you will have H3C, C, CH. Now the question is, from where do I remove hydrogen? If I use Sator's rule, I'll have to remove hydrogen from that carbon atom containing less number of hydrogen atoms. So because, no, see, this is the, from here I'm removing bromine. That means the hydrogen atom either has to be removed from this carbon atom or this carbon atom. From the carbon atom adjacent to that carbon atom from where bromine has been removed. So either it has to be this or it has to be this. This has got 2 hydrogens, this has got 3 hydrogens. So you will remove it from that carbon atom containing 2 hydrogens. So in that case you will get this as CH, double bond comes here, CH3. Right? So this is going to be sec butyl bromide. This is going to be, this I have removed now, dehydrogenation. So potassium bromide and dehydrogenation means water molecule has to come out, right? So this is sec butyl bromide. This particular compound, 4 carbon atoms, therefore but, double bond, therefore ENE, double bond is attached to the second carbon atom, therefore 2-butene. And do you get the sec here? So what you get is called as 2-butene. Those of you who want to write the Sator's rule down, please write it down. The spelling is SAYTZEFF. Sator's rule is applicable, right? Guys, Sator's rule is applicable only in the case of higher alcohols and alkyl halides, right? So right, in the case of higher alcohols, and alkyl halides, in the case of higher alcohols and alkyl halides, hydrogen atom from the adjacent carbon atom, carrying less number of hydrogen atoms, is preferentially removed to form a highly substituted alkene. Next, what happens when tertiary butyl let's see another reaction, guys. What happens when tertiary butyl bromide reacts with alcoholic KOH? KOH alcoholic, right? Tertiary butyl bromide. Tertiary where a carbon atom is connected to 3 other carbon atoms. So this is my tertiary carbon atom. Butyl, 4 carbon atoms. Bromide, this is my tertiary butyl bromide, reacts with KOH alcoholic. This is tertiary butyl bromide. Right? Now, in which case, first of all, you will have dehydrogenation. So that means KBr. Potassium reacts with bromine. Now, in this case, I cannot use Sator's rule because if you look at the carbon atoms adjacent to the tertiary carbon atom, all of them have same number of hydrogen atoms. If those carbon atoms did not have the same number of hydrogen atoms, then I could have used Sator's rule. Since all the three adjacent carbon atoms have same number of hydrogen atoms, therefore there is no need for me to use Sator's rule here. So in that case, I can remove it from wherever I want. I can remove the hydrogen atom from wherever I want. First of all, I'll form water molecule. This will be CH3C, CH3 double bond CH2. I could have removed it from anywhere. Right? Now, this 4 carbon atoms, therefore BUT, double bond, therefore YLENE. Since if this is my primary chain, I have a methyl group in the branch, therefore iso. So this is going to be isobutene. Fine, do we get this thing clear?
So that is?
Excuse me? BUT because there are 4 carbon atoms. ENE because there is a double bond. So this is butene. And isobutene. You have this in the branch. That's the reason why it's not isobutene. That was if it was a primary compound. If it it was a straight chain compound, then I would have written that. Right? Next, let's consider we did elimination reaction. The next kind of reaction that we will do is Ward's reaction. Now, what is Ward's reaction? It is a reaction of alkyl halide with active metals. When alkyl halides react with active metals in the presence of dry ethers, they give you a higher alkane. When alkyl halides react with sodium metals, they give you a higher alkane, and this reaction is called as Ward's reaction. I will illustrate this with the help of equation. What happens when ethyl bromide reacts with sodium metal? Ethyl bromide reacts with sodium metal, right? Ethyl bromide, CH3CH2, ethyl bromide. Observe carefully, reacts with sodium metal. You take 2 atoms of sodium metal and react it with 2 molecules of ethyl bromide. I'm going to write ethyl bromide instead of writing 2 ethyl bromide. I'll show you the 2 ethyl bromide separately. So this is Br CH2 CH3. So the 2 Brs will react with the 2 sodiums to form sodium bromide 2 NeBr plus CH3 CH2 CH2 CH3 CH3 CH2 CH2 CH3. This was ethyl bromide, and there you get 4 carbon atoms, that is butane. Right? Ward's reaction is a method of converting alkyl halide into alkane. What is Ward's reaction? It is a reaction where alkyl halide is treated with an active metal to form a higher alkane. Alkyl halide is treated with an active metal like sodium to form a higher alkane in the presence of dry ether. Dry ether is used as your catalyst. Fine, do we get this thing clear? The limitation of this particular reaction is that you will get a higher alkane containing even number of carbon atoms. You will get a higher alkane containing even number of carbon atoms. Fine, do we get this thing clear? And methane cannot be prepared by this method. 2 drawbacks of this method. A, you get a higher alkane, you getting only even number of carbon atoms. So if I want an alkane having odd number of carbon atoms, I cannot use Ward's reaction. Second, Methane cannot be prepared only using this method. See, I'll show you another reaction of Walsh reaction. What happens when methyl iodide reacts with zinc? Methyl iodide with zinc, right? Methyl CH3I reacts with zinc and ICH3. I'm using 2 methyl iodides. Why am I not using 2 zincs? Because zinc valency is 2, so I don't need 2 atoms of zinc here. So this is methyl iodide dry ether. So zinc will react with iodine to form zinc iodide plus CH3CH3. Right? So then in which case you will get this as ethane. Fine? So do we understand Walsh reaction? Next, let's see the formation of Grignard's reagent. Formation of Grignard's reagent. Now first of all, what is a Grignard's reagent? A Grignard's reagent is organo-magnesium compound. It is an organohalide, right? So its general formula is RMgX, alkyl magnesium halide. Fine, do we get this in here? How do I prepare a Grignard's reagent? Grignard's reagent is prepared when pure and dry magnesium metal reacts with alkyl halide in the presence of dry ether. For example, if I tell you what happens when methyl iodide is treated with magnesium. What happens when methyl iodide is treated with magnesium, right? Methyl iodide CH3I reacts with magnesium in the presence of dry ether, right? You will have addition reaction taking place. Addition reaction, 2 or more reactants combine together to form a single product. So you will get methyl magnesium iodide plus heat energy, right? It's an exothermic reaction. You will have some amount of heat energy that will be released. So this is methyl iodide and this is methyl magnesium iodide, right? So thus, what is Grignard's reagent? It is alkyl magnesium halide, right? It is RMgX, alkyl magnesium halide. It is an organo-magnesium compound. It is made by reacting an organic halide with magnesium. Fine. And the reaction takes place in the presence of dry ether. Fine. Next, let's see another reaction of this kind. What happens when ethyl bromide reacts with magnesium metal, right? So in this case, ethyl bromide CH3CH2Br reacts with magnesium in the presence of dry ether, right? You will have addition reaction taking place. So you will have CH3CH2MgBr plus heat, right? This is ethyl bromide and this is ethyl magnesium bromide. Fine, do we get this thing here? So you get ethyl magnesium bromide. Where do I use Grignard's reagent? Why am I studying about Grignard's reagent? It has a wide application in preparation of different organic compounds. A large number of organic compounds can be prepared by using Grignard's reagent. For example, alcohols, aldehydes, ketones, carboxylic acid. Most of these compounds can be easily prepared by using Grignard's reagent. What is the limitation of using a Grignard's reagent